So today we're going to talk about a one sample interval for the proportion. So previously in chapter 8, we learned how to find a 1 minus alpha level confidence. This is C%. So level of confidence interval for a population mean, using a Z distribution. In this section, we will be using similar ideas to create a confidence interval for a population proportion or percentage, Population proportion in this case, Population proportion is P. In population proportions, there will be no mention of a mean or average. Instead, we will be looking at the proportion or percentage of a group of individuals that represent a success. The number of successes x out of n trials, where p is the probability of success, is a binomial random variable, And we talked a little bit about this from chapter 4. Now, recall, we write, the random variable is distributed, a binomial, distribution, where n is the number of trials and p is the probability of success. Since we do not know the population proportion, we are trying to estimate the probability of success p from a sample. This estimate of p is called p hat. So to find p hat, and let me just write it a little bit differently. So p hat. So p hat is equal to x over n, where p hat represents the proportion of successes in the sample, So x is the number of successes and n is the number of total trials. So let's state and check the assumptions for a confidence interval. So the first one is a simple random sample of size n is taken. B is the condition for the binomial distribution are satisfied. And so C, to determine the sampling distribution of p hat, you need to show, so n times p hat and n times q hat is greater than or equal to 5. And then just remember, where q hat, this is the failure. So if p hat is the successes, q hat represents the failures, and it's just 1 minus p hat. If this requirement is true, then the sampling distribution of p hat is well approximated by a normal curve. Now, in reality, this is not really true, since the correct assumption deals with p. However, in a confidence interval, you do not know p, so you must use p hat, So we don't know the population proportion, so we're using the sample proportion. That's what it's saying. So really what we're just needing to show is that the number of successes is greater than or equal to 5, and the number of failures is also greater than or equal to 5. So if you have a large trial, usually you're good. So when n is large and p is not close to 0 or 1, we can use the normal distribution to approximate the binomial. That allows us to use a normal distribution to create our confidence interval for our population proportion, So normal distribution is just our Z distribution. Okay, I know that's lots of information here. So really, as long as our assumptions are met, what we can do is find a confidence interval. So a C% level of confidence interval for P is given by, so it's P hat minus E and then P hat plus E. And so again, we're going to create this interval. So P hat plus or minus, the margin of error. So where P hat is the sample probability of success, Q hat is the sample probability of failure, N is the sample size, Z of C is the critical value, and E is the margin of error. Remember, our book and homework like to use ME for the margin of error. So here's my margin of error formula. And so as long as I have P hat, you can find Q hat by subtracting it from 1. And then again, the margin of error is sometimes also called the EBP, the error-bound proportion. So let's take a look at our first example and find a confidence interval. So it says, suppose we want to know the true proportion of voters who plan on voting for Clinton in the upcoming election. We take a sample of 1,500 registered voters and find that 702 plan on voting for Clinton. Find a 95% confidence interval for the true proportion of voters who plan on voting for Clinton. Interpret your answer. All right, so sample size, So sample size is 1,500. 702, That's successes. So failures, if you think, are definitely, we need to make sure that they're both greater than or equal to 5, which in this case they're, since the successes is 702, failures is definitely going to be greater than 5. Confidence level is 0.95, So you could say, if you remember, your critical value is 1.96, That's one that we should have memorized. If not, you can go through and create your table and still, use inverse norm to find that. So what we're trying to do, right? We're trying to find, right, p hat plus or minus the margin of error. So the first thing we need to find is the margin of error, right? Which is, if you look at the formula above, right, z of c times the square root of p hat, q hat, all over n. So we're missing a couple things here, right? We don't have p hat, so we first need to find p hat. So p hat is equal to x over n. So in our case, x was 702 and n was 1500. So 702 divided by 1500 is going to give me, right, 0.468. And now q hat is equal to 1 minus p hat, right, the percentage of failures. So 1 minus 0.468 will tell me, right, the percentage of failures, right? So those that did not vote for Clinton, if we put it into words. All right, so 46.8% voted for Clinton, 0.532 or 53.2% did not vote for Clinton. Okay. So we're ready to find my margin of error, right? So margin of error, I have 1.96 times the square root of 0.468 times 0.532 all over, right, n, which is 1500. Okay. So in order to type this in, it's pretty straightforward. You can just sort of type it in how you see it. So 1.96. I'll hit my square root button, and we have 0.468 times 0.532 divided by the 1500. And I always like to keep an extra couple decimal places when we're dealing with error and then round at the end. So 0.025, I might say 25. So that's my error. Okay, so I'm ready now, right, to create my confidence interval. So I'm going to take, right, p hat minus e less than the population proportion and p hat plus e. So we said, right, the sample proportion p hat was 0.468, right, minus the error of 0.02525 less than the population proportion, right, and 0.468 plus 0.02525. And then at this point, I might actually round to like 3 decimal places. So 0.468 minus 0.02525. So let's see, 0.443. And then I have 0.468 plus 0.02525. And we end up with roughly 0.493. Okay. So that's my confidence interval, right? That's, if we were trying to find that, that's my interval. But let's interpret that, right? So we can say we are, and maybe you could even just say we are instead of we can say, we are 95% confident that the true proportion of voters who plan on voting for Clinton is between, so we could say 0.443 and 0.493. Oops, sorry, let me move that up. And so sometimes too, they will write it as a percentage. So you could even say 44.3% and then 49.3%. Okay. So again, I found my margin of error, right? I first had to find my sample proportion, margin of error. Then I found that confidence interval. Like the last section, you can actually find the confidence interval in your calculator. So again, if you hit your stat, you go over to calc. So you have your stat button, you go over, sorry, to tests, not calc, tests. And so what we want, right, so we're going to go down a little bit farther. We want the one prop z interval. Lots there. So the one prop z int, right? So it's the one proportion z interval. And we'll hit enter. So it asks for x, which in our case was 702. N, right, was 1500. And then it asks for the confidence level, which in this case was 0.95. And so if I calculate that, you will see, right, that we have 0.443 and 0.493, right? So we actually find that same thing. It also tells you the sample proportion. So how we found that in, our first step, it'll re-say that. So again, as long as the question is asking for your confidence interval, you can actually use your calculator to find this. If it asks for a specific margin of error, right, you could go through and sort of do it by hand. But that is our first example of a confidence interval with a one sample proportion z